So I'm switching on the recording, and with this I'm ready to start. Last time we completed the discussion of the Cauchy's problem for the ordinary differential equation. Well, it's not possible to complete this discussion, but we had to stop. Better to say that, because the topic is so deep that it's possible to talk about that for the whole semester. Let me check the numbering of our chapters. So, last chapter was number 4, the ordinary differential equation, Cauchy's problem, and now today we are starting chapter number 5. Chapter 5, 2-point boundary value problems. For the ordinary differential equations. So we are still dealing with the ordinary differential equations, but we are starting to talk about the boundary value problem instead of the initial value problem that we dealt with before. So, what is a boundary value problem? Have you ever came across such kind of problems before? What do you say? When? How about you? Charles says she did not. Probably she just doesn't know the name.
Yes, maybe.
No answer from Wang either. Let me introduce an example. Then. So let's take a mechanical example. We have a beam. Say we are building a house, and we want to know how tall should be the beams that connect to walls, to opposite walls. Suppose we are making a floor, and we want to know how often we should put our supports to prevent excessive bending of the floor under our weight. But this problem will be simplified or idealized. So we have a beam, a single beam, on 2 supports that allow for free rotation. They only provide support from the bottom and prevent beam from falling down. And also, at these points, the beam is fixed from the horizontal movement. And we are loading our beam with a uniform load. Well, it can be non-uniform as well, so we can generally say that the load is Q, depending on X. But for this particular example, we'll assume it's uniform. And what else we need to know? We need to take into account the cross-sectional shape of our beam. Suppose we cut it at some point, and this is what we'll see. This is the height of the beam, this is the width of the beam, and the moment of inertia is a mechanical characteristic of any object, of any solid object, or elastic object. For this particular case, if we have this simple cross-section, well, it is just a mechanics course. I don't know if you had this mechanical course before. Okay, you had it. Very good. So, this is the moment of inertia. And if we want to know the deflection will be defined by a second order differential equation. Suppose the deflection, we denote the deflection by W, then the equation reads the second derivative of this W taken with the negative sign plus plus some quantity that I will just explain in a second. This S is the force that's applied. Suppose we are applying a tension force on the edges of our beam. So if this force is present, then this term will be present as well in the equation. And E is another characteristic of the material. It is a Young's modulus. Young's modulus. The dimension of this Young's modulus is Pascal, or better to say Newton divided by meter squared. What else I need to define? And just for your reference, the dimension of this Q is Newton's divided by meter. So it is a force intensity, so to say. So we divide it by the length of the beam. What else? The deflection is measured in meters. Anything else? That's unknown. So, what's Young's modulus? Young's modulus defines how large will be the deformation of an elastic object under a load of 1 Newton, for example. If we load an elastic object with some force, this elastic object will become longer in the direction of tension, and then how much longer it depends on the value of this elastic modulus. So this is the left-hand side of our equation, and on the right-hand side we are going to have something like this. X L minus X, where L small is the length of my beam, the total length of my beam. So again, what we are having here, this is the ordinary differential equation again. We have only one function. We want to know W. Actually, it's not a constant, it's a function of x, because the deflection will depend on the coordinate. The deflection at the edges is equal to what?
S?
No. The deflection W at this point and at this point. What is the deflection at this point, for example?
Omega?
W.
Yes, W.
What, can you say what this is equal to?
If we start from this point, it will be 0 or not?
It is always 0, because this is a support with free rotation but no movement. It's a fixed support.
Okay.
So we can say that W of 0 is 0 and W of L is also 0. So we need to find such function. We need to find such function W of x that is sufficiently smooth, meaning it should have the second derivative at least, that is sufficiently smooth, and it makes this equation a true equality. So if we substitute it here, it becomes true equality. And also this function should satisfy these two conditions. Unlike the previous case with Cauchy's problem, we do not define our conditions on one end only. If we solved a Cauchy's problem, we had to define, for example, the value of the function, the W, and its derivative at the left end. But now we are defining two values at different ends of our beam. And this kind of problems is called boundary value problems because we are defining our value at the boundaries. These are the boundary conditions. In this case that we are currently considering, these conditions are pretty simple. This is a so-called first type, or Dirichlet, French mathematician, Dirichlet, boundary conditions. Second name of French mathematician of 19th century.
Dirichlet equation or interpretation?
Excuse me?
Dirichlet equation or
Dirichlet boundary conditions.
boundary.
Boundary conditions. This kind of boundary conditions is called Dirichlet conditions because he first considered this type of conditions. And it's not the only possibility that we can have. We can actually have second type boundary condition for some specific problem formulation. We can define this condition of second type. For example, on the left hand, let's imagine that we have it on the left hand. The condition will look like this. The derivative of the function w at the point x equal to 0 is some predefined value, is equal to some eta 0. And very often this eta 0 is equal to 0 itself. And in this case it will be called the Newman boundary condition. Newman boundary condition from Newman. Okay, and it's also possible to have a combination of the two, of the first and the second. It's going to give us a third type condition, like let's say plus dw by x plus some a, some constant a by w. All this is taken at the point x equal to 0. It is equal to some eta gamma 0. So it is another possibility.
Is constanta
A is just a constant. This A is just a constant while we are considering a two-point problem. It should be just a constant. Oftenly it is just one, but the physics may define some other value. So all these possibilities define different boundary value problems. If we only have this type of conditions, we say that we have the first boundary value problem, or the second boundary value problem, or the third. By the way, you have to be careful with the second boundary value problem. If you want to impose this condition on both ends, what it actually means if you impose this type of condition. In mechanics, they prove that the derivative of the deflection is the rotation moment. This is the rotation moment, physical meaning of this quantity. And if you define only the rotation moments on two ends, you do not define the position of your beam. If you define this condition on both ends, it will mean that you do not say where your beam is placed in the space. You only say that you apply some like rotative force to bend it, but where it happens in the space, this is not defined. And in such a case, if you do not define at least this or this condition, at least on one end, then you will have a problem with convergence at least. And strictly speaking, or mathematically speaking, you will have a problem with existence and uniqueness of your solution. The solution will be, may be non-unique. Many different positions of your beam in space will define the right solution. That's why this type of condition is typically defined only on one end.
May I ask you a question?
Sure.
How can we differentiate, like, how can we find that this is the, like, we are seeing the problem, and how can we say it's like first type of the boundary condition or second type of?
Well, I'm not sure I know what you actually mean by your question, but I will try to assume. So here on this class, we are mostly solving mathematical problems. So we should have a problem formulated in as a mathematical equation with some boundary conditions, and it's a matter of physical meaning how you obtained these boundary conditions, right? So in physics, for this particular problem, if you have to fix the position, it will most likely be the first type condition, right? If you simultaneously fix the position and apply some rotative moment to one of the end at the same end, then you will have the third type boundary condition, because you need to define both the moment and the position. If you only say that you apply the bending moment on this end, for example, you don't apply anything, you remove this support at all. You can remove this support, and you will need to define the moment here, otherwise the beam will just rotate, and that's it. Under the load, it will rotate forever.
Yes.
If you do not fix this end, right?
Yes.
So, if you impose the correct condition on this end, it's possible to remove this support, but you have to put something, mathematically you have to put something here, and this something will be dw by x is equal to 0. It means that we do not apply any moment at the right hand side, and we do not fix its position. It corresponds to the case when we have a console. You have a wall like this, like this brick wall, and you have a beam that's embedded into the wall, and it extends to the space here. So suppose it is only loaded with its own weight, and you will need to know its shape, how it will bend under its own weight. Then you will have the case when on the right hand side, on this free end, you will only have the second type, the zero second type boundary condition, minimum condition. Okay, let's continue. So this was just an example to feel what kind of problems we are solving.
Yes.
And I will delete this example from the board. And we'll formulate the general problem, problem formulation. So in general, we can say that we have some function. We want to find some function u of x, which is defined by this differential equation. Phi is some nonlinear function, very general nonlinear function. It depends. It may depend on the free coordinate. It may depend on the unknown function itself, and it may also depend on the derivative of the unknown function. And for the boundary conditions, we will also introduce a very general case. So a0 is a constant. It's multiplied by the value of function u at the left-hand side. Well, to define the interval from a to b. Suppose we are considering the solution at the interval from a to b. So this will be u at the point a minus a1 by u derivative of u at point a, and this should be equal to some constant eta a b0 u of b plus b1 u derivative at point b is equal to eta b. And we need to say that these constants, the sum of their absolute values is not equal to 0. So at least one of these terms is present. And the same thing about the b coefficients.
Why we need this coefficients? Why we need this coefficients?
Because we need to have either the value of the function defined at the left and at the right hand side, or the derivative of the function, or both.
Okay. So like so
This is exactly just in the previous just as in the previous example. And also a0 multiplied by a1 is more than 0. b0 multiplied b1 is more than 0. So these coefficients are positive. So the function phi is defined in the following set. Is defined in the following set. X u derivative. So x is from a to b. U can be from minus infinity to plus infinity, and the same for the derivative.
D is the solution. D is the solution.
No. This is the set of points where this function phi that sits on the right hand side of our equation is defined.
Okay.
Should be defined.
So
Function phi is defined on the following set. So what we need to ensure what conditions this phi should satisfy to let us be sure that the solution exists and it is unique. Let us recall what we asked from the right hand side in case of Cauchy's problem before. What were the conditions for the Cauchy's problem? Do you remember? So not any function phi is valid for us. We should impose some restrictions on function phi. Wendt, are you here?
Yes, but
Can you recall the conditions? What conditions function phi should satisfy?
but I can't see your very clear. Yes, can it? Oh yes, it can be.
Sorry, you should have told me earlier because I just forgot to resize
Okay.
resize the image. So the condition was very simple. Function standing on the right hand side for the Cauchy's problem case had to be only Lipschitz continuous on its second argument. When we talked about the normal system, where on the left hand side we have the first derivative. Lipschitz condition was like this. So the difference between the second arguments must bound the difference between the function values calculated at these two different values of the right hand of the second argument. This was a very simple condition, and many functions satisfied this condition. Boundary value problem is much more complicated. Object is a much more complicated object, and we have to impose much stricter requirements on the right hand side. Let me formulate these requirements right away as a theorem of existence and uniqueness of the solution. So let phi of x u derivative is continuous in D on the set of points D, and let phi, the derivative of phi by its second argument and the derivative of phi by its third argument are also continuous in D. And if first the derivative of phi with respect to its second argument is negative, in this case where we have the minus sign before the second derivative. It's important. If it's possible to put plus sign here, then this condition should be inversed. If this derivative is negative for all values of arguments in D, and if the derivative of the right hand side by its third argument is bounded by some constant m for all points x, u dash, no, it's not dash, asterisk. How it's called? Hyphen. It's called hyphen in English. I'm sorry, I'm forgetting words. Then the solution of star, of the problem star, exists and is unique for any boundary conditions. Well, I'm not going to prove this theorem because it's a matter of the differential equations course to provide the proof of such equation. But we have, before solving the problem, we have to think whether we can guarantee that the solution exists and is unique, or we cannot guarantee. What happens if we see that our problem does not satisfy these conditions. Can you tell me what happens? What should we do next? If we take the problem and see that it does not satisfy these conditions, what's our next step? Let's think about this problem. Does it satisfy the conditions of the theorem or not? When, if you have something to say, please do it.
So you have
What is phi in this case? What is phi?
minus
Phi is equal to what?
minus 3 or minus 2x squared over 2. Am I right?
How do you...
Minus new?
Sure.
This is minus new just.
Minus u, you are saying. Minus u.
Yes.
Why minus u? Why are you saying minus u?
But you said
Look here.
that we don't do use minus 2. It's like
Minus second derivative is in our general formulation, right? On the left hand side. Here we have plus. What should we do first?
just
To reformulate the problem in the standard, into the
just
standard
putting
shape.
minus.
Well, if you put here and here minus, it's gonna be the same equation, right? Well, what's next? How to say what is the phi function? The right hand side. What is the right hand side?
So right hand side maybe
What should I write here? Nikita?
it's like
Just you?
Just u. Exactly.
Yeah, yes.
We do not have x here. We do not have
okay.
u, the derivative of u here, u hyphen. We only have u. Okay. What is u, the derivative of phi by u?
1
It is 1. What is the derivative of phi by u hyphen?
0.
0. Cool. Can anyone tell me what conditions are satisfied and what conditions are not satisfied with respect to this theorem?
So with respect to this theorem, the first is not satisfied.
The
because-
first is not satisfied.
Yes.
Not satisfied.
And
This
also-
is satisfied, right?
Yes.
It's less than, for example, 1. But it's not sufficient because this condition is fails. So we cannot say that there is a unique solution for any boundary conditions. We cannot say that based on this theorem. And that's it.
Yes.
We are not saying that the solution does not exist. It's important to understand. We cannot say that the solution does not exist.
Right.
Okay? And it's easy to demonstrate that for this particular problem, the solution exists. How to demonstrate that? Wang, can you solve this equation? Who can solve this equation?
What kind of
This differential equation.
is it like for the x or just for the u?
This is a matter of ordinary differential equations course, mathematical course. So, we need to write a characteristic equation, for example. One way to solve it is to write a characteristic equation. Characteristic equation is what? It is our assumption that we can search for, well, I will not derive it, that we can search for the solution as the exponent at some power. And if we substitute it here, we will get the characteristic equation of this kind. And we need to solve it. The solution will be?
This is the like
Oh, I'm sorry.
quadratic.
I'm sorry.
It's like
Yes, because this is the second derivative, there is no first derivative, and the free term corresponds to this one. So, this is plus minus I, or plus minus square root of minus 1. This is the solution. And the theory says that in this case, our exact solution, the general solution, will have this form. Some constant multiplied by e, well, actually by e to the power of I plus constant by e to the power of minus I, ix actually. This will be the general solution. Or it can be rewritten in the following form. It's possible to show as well, but I just don't want to spend time for that. It's cosine plus another constant by sine of x.
e sin
Hmm? No.
x.
Well,
Yeah, I
you
know
can-
this like exponential equation.
if
Yes.
if this e to the power of ix is a
Yes.
solution, and this is a solution as well, the theory says that you can combine these solutions and get another solution. So if we denote this by u1 and this by u2, we can construct another u1 by making this. Okay? And we can construct yet another u1 by making, let me check, 2 by 2i, e minus e by this combination. And this is how you can prove that this form is equivalent to this form. You will need to recall what means exponent of a complex
X,
function. I'm sorry, x should be present here. Okay, but this is true. And what are the values of the constant c1 tilde and c2 tilde? This can be recovered from the boundary conditions. Where are our boundary conditions? I did not say yet what are the boundary conditions, because I wanted to demonstrate that for some choice of boundary conditions, it is possible to find the exact solution, and for some other choice, it's not possible. Let's, for example, say first variant of the boundary conditions. Let's say u of 0 is equal to 0, and u of pi is equal to what I want it to be equal to 1. If u of 0 is equal to 0, we take this equation and find the constants. Let's take this equation. At point 0, sine is what?
C1,
Sine of 0 is what?
0.
Is 0. Then cosine of 0 is 1, right?
So
Then
C1
C1 tilde is what?
0. 0.
Is 0.
Right.
Then from the second condition, what do we have?
Minus 1.
Pi. Pi, again, sine is 0,
Right.
right? But this cosine is again 1,
Minus
but
0.
yes, minus 1, you're right, for sure, minus 1. Then C2 is not possible to recover from here, but
Yes.
the second point says that C1 is minus 1.
Right. Right.
Do you like it? C1 is 0 and C1 is minus 1. It's impossible, so contradiction. No solution. So in this particular case, we cannot find a solution. There is no solution that satisfies these boundary conditions. Okay? Let's change boundary conditions. How do we change it? For example, we can say u of 0 equals 0, u of p by 2 is equal to 1. Yeah. So this guy gives us the same answer. This guy, what it gives us? If x is equal to pi by 2,
C2. Right. Asterisk.
yes, C2 is equal to what?
C2 is equal to 1.
Is equal to 1. And in this case, the solution will be 1 multiplied by sine. So mainly sine. We could find the solution. So even if you check the existence by this theorem, it does not mean the solution does not exist, but it just does not exist for any choice of the boundary conditions. For some choice it may exist still. Okay, let's move on. Do you want to check another example?
I think it's enough.
Okay, it's enough. Then we'll have it on the exam. Okay. The next, so we discussed the general boundary condition or the general boundary condition, boundary value problem, and for the following discussion, let's switch to the linear case when the right-hand side is a linear function. This is a pretty important, well, I don't remember. We're still in the paragraph number 1, right?
Chapter 5.
According to my numbering, I have paragraph number 1, point 3, linear boundary value problem. So in this case, the equation may be written like this. Why this is called linear? Because the derivatives, all the derivatives and the function itself, the unknown function, are present in this equation linearly. Okay? So, what? Let us reformulate the theorem. Oh, I shouldn't write in Russian, I should write in English. Corollary. Corollary. It is just a corollary from our theorem that was written here.
Yes.
So, what conditions should we request from these functions? What should be these functions?
It's like it's less than 0 or something.
What function is should be less than 0 or more than 0?
Should be less than whatever is like phi function. Or like
What is phi function in this case?
here phi function is like d over dx.
Not only this.
Quick.
All these guys should contribute to the phi function.
Okay.
And if we move them to the right hand side, then the first requirement was
Plus a minus, and so that's why you have larger than 0.
so what you're saying.
It's not,
Okay.
we not divide x.
Just
When could you say it again, please?
I say we first put all of them on the right side and divide. Not divide. Is I don't know what to say. Is
We find the derivative of the function
Yes,
phi
yes, yes.
by u, right?
yes, yes. By
And
u.
what is the derivative of function phi by u?
By u is minus qx.
Minus what? Minus r of
Qx.
x, right?
Yes, yes.
It should be less than 0,
okay.
because this is the derivative of phi by u.
R where is the R?
This is r. Well, I'm writing r differently in different places. So this is r of x. Function r minus function r should be less than 0, then it means that function r should be more than 0, strictly.
Yes, I also talk like this.
Sorry, I didn't recognize that. No. So this guy should be more than 0 if it sits on the left hand side, and should be less than 0 if it sits on the right hand side, taking into account the coefficient before it. So, do we have any condition on this guy?
QE and QX is like less than m.
There should exist some constant m, such that the absolute value of this function does not exceed this constant. What it means physically, let's imagine some physics interpretation, or let's develop a physics interpretation. This is a channel. This is a channel with a flow of some liquid. And suppose at the left hand side we define the temperature of this liquid, T0, and on the right hand side we define the temperature of this liquid, T1. So, for example, this can be some technological process of making a concentrated milk. So you have a milk flow along the pipe, and here it is hot, and here you want it to cool down to temperature T1. You know the velocity of your milk along the pipe. And the pipe can be non-uniform, can have a non-uniform shape. It can be narrower or wider at some points. This is why this velocity q of x is different depending on x. It depends on x. Okay? So this q has a meaning of velocity. What is r? U is our temperature, actually. Well, I should have written U0 here and U1 here to keep the same notation. What are these U's? These values are known, and we want to find the temperature distribution as a function of the coordinate. How quickly our concentrated milk cools down, and at which particular cross-section it reaches some predefined temperature, for example. We want to know it. So, what this term will mean physically, and this term, what they will mean.
Physically?
Yes. What's the physical meaning for this particular example with milk?
Is the length or not?
No. Well, U is temperature, right? We want to find temperature. This equation defines the heat transfer. It's a combination of diffusive heat transfer, actually, because this is the diffusion. This term defines diffusion along the pipe. If we had zero velocity, we will still have some temperature distribution along the pipe because of the diffusion. Heat is transferred molecularly by molecular motion to subsequent layers of the medium. Okay, so this is the diffusive term. This term is called convective term. And depending on the application, this term can be called a reaction term, or in this heat transfer example, this term becomes, if I put it to the right hand side, it becomes a heat source. Oh, this guy is a heat source that depends on the solution itself. So this part does not depend on the solution. It means that you are pumping in or out the energy from the system. So you can heat up your milk as it flows along the pipe. And you can heat up it differently at different X locations. Or you can cool down. You can have coolers around this pipe, and those coolers take the heat out of the system. So, but this heat source or sink will not depend on the solution itself. But it's possible that that heat source or sink depends on the solution as well. Why? Well, if it were not a milk, but some radioactive liquid, it could produce heat just during its lifetime because of radioactive processes in this fluid. Or it could be a chemical process, which can also depend on the temperature. Chemical processes usually heavily depend on temperature of the reacting species, right? So, if you have a situation when your temperature grows and this coefficient, if it was negative, if R was negative and minus makes it positive, if this whole coefficient was positive, then it would lead to explosion of your system, infinite growth of temperature, because the higher the temperature, the more heat you are pumping into the system. If this guy is positive, then uncontrollable heating. You see it or feel it?
Yes.
that if we have positive value of this coefficient, then we'll have an uncontrollable heating, which is bad, and which is mathematically complicated. That's why we are requiring that this whole term is negative to prevent uncontrollable heating, meaning the higher the temperature, the smaller the contribution from this temperature-dependent heat source. Okay? So this is the physical explanation, and for me, personally, it allows me to easier remember this condition on the sign of this coefficient. Okay, let's continue then. What methods can we apply to solve this kind of problem? Let's discuss the methods.
Method?
Yes, we are talking about numerical methods to solve various problems formulated as differential equations, so we need to discuss the method to solve this particular problem. I'll delete everything we don't need. Shooting метод. По-русски метод стрельбы называется. Shooting method. So we can consider, actually we could consider a general problem, but since we started with this problem, let's continue with this problem. So let's say that on the left hand side I'm fixing the value of function u, and on the right hand side I'm also fixing the value, just for simplicity of discussion. The idea of this shooting method is to replace the solution of the boundary value problem with the solution of several Cauchy problems. The boundary value problem says that we want to find such function u that is equal to ua at point A, and that is equal to to ub at point B, and it depends somehow on the unknown, on the independent variable x. This we want to find. What tools we can apply to find functions? We know Cauchy's problem solution methods, but for the Cauchy's problem we need to have two boundary conditions on the left hand side, because this is the second order equation. Since this is the second order equation, we have to have two boundary conditions on the left hand side instead of two boundary conditions on different ends. So this condition is perfectly fine for the Cauchy's problem formulation, but this condition is not fine. We don't know how to deal with this. That is why we reformulate our problem. So we keep this equation unchanged. I will just mark it somehow with green line and say that we still have this green equation here. It is the same, just to avoid rewriting. Okay. And for the boundary conditions, we have the same condition as in the original problem, but the second condition has to be changed. instead of the second condition from the original problem, we introduce the condition for the derivative of the function u. We say the derivative of function u is equal to some parameter s. What it means geometrically? It means that we start from this very point and we choose some angle, for example, like this, some angle alpha, such that tangent of this angle alpha is our s. Because when we say that derivative of function u at point A is equal to something, we are defining the angle at which we want to start. The derivative is just an angle. Okay? And this is why the method is called shooting. This is like we start a ball at this angle from this point, and then we will follow our equation along the trajectory. Using one of the methods we discussed before for the Cauchy problem solution. So when we use this method, we finally end up at some other point, u say 1 of b. So this will be our first trial to shoot. Okay? And we did not hit the target. Target is here. We want this value. But we actually ended up at this value. What should we do next? How? What should we do with our how to say that in English? Вспомогательное. Additional. Let's call it an additional Cauchy's problem. So what should we do with our additional Cauchy's problem to get closer to this point? How should we modify our problem 2 stars to force it generate the solution of our original problem?
Find the difference of 2 points or something, or use.
Very good. So you can define some function psi that depends on this parameter s actually. And this function will be, for example, the difference between ub and b of s. So this ub of s is the solution of the Cauchy's problem with the parameter s for this condition, for the second artificial condition. Okay? And you want this guy to get to 0 choosing s, choosing parameter s. By choosing parameter s, you make this penalty function to tend to 0. Okay? Follow the. We formulate a penalty function which actually is a difference between the result we want to get, between the value of our unknown function on the right hand side that we want to get, and the result that we actually obtain with our artificial or additional Cauchy problem solution. Okay? We solved this problem and found that we are still far from our goal. Then we say this is the penalty, штраф. Okay? Функция штраф. And but we define this function, and then we use some algorithm to adjust parameter s so that we get closer and closer to the value ub at the right hand side. How can we adjust? What are the options to adjust the parameters? We can use, we can minimize this function by using, for example, by using Newton's method. Newton's method for nonlinear problems, for nonlinear equations, algebraic equations. How the method will look like, or what the method will look like. Let's say we started from some s0, from some zero value of this parameter, and the next value can be calculated from the previous value according to the following formula. Psi of s, psi of sk minus 1 actually, of previous parameter, divided by the derivative of this psi with respect to s, computed at the previous value of this parameter. And this is the tricky part, the derivative of psi with respect to s. We do not have this derivative analytically. And one trick that's typically used is to compute this derivative numerically using the methods that we discussed before, numerical differentiation in the beginning of our course. So what do you need to compute this derivative numerically? When? Are you still here? Are you following?
I'm still here, but
That's good, but are you following our discussion? So, do you understand what this function psi means?
I understand. Yes.
Okay, so did you get the idea about, actually we can talk about this problem as minimization problem, or we can just say this psi of s should be equal to 0 as a nonlinear equation solution problem.
Is it about the error in the computer?
This is
You get it.
This is the error between the result that we obtained using our artificial Cauchy's problem that we introduced and the result that we want to obtain.
Okay.
This
Okay,
difference,
understand.
psi of s. And we want this psi to be 0. How can we ensure this? We need to solve and find the root of this function, find the value of s, which makes this function 0. How to do that technically? This is usually discussed in numerical mathematics courses, and one method is the Newton's iteration method. Newton's iteration procedure is written here. It depends on the first value or 0th value of s, and it defines the next value in terms of this previous value and the value of the function psi divided by its derivative by s. So the tricky part of that, as I said, is to compute this derivative. How to compute this derivative? You can do it numerically. For example, you can take the value of function psi at the previous value of s, and you can add small variation to this guy, and then you can take the original value and divide it by this variation. This will be approximation to this derivative. What means this operation? What this operation means? How to compute psi from this argument? What should we technically do?
It's like error. Delta.
Psi. We defined it by this absolute value of this
Yeah, I
difference, right? But we don't know analytical form of it because we don't know the analytical form for our solution. Okay?
Yes.
We're using numerical methods. We can only calculate the number, the value of psi when we put some particular number here in the brackets, some particular value of s. We take some value of s, then we solve this Cauchy's problem. We subtract the right-hand side value that we obtain from the value we want, and this is how we get the value of function psi. Okay? So my question is, what do we need to do to compute this term, this first term? What do we need to do?
Can we just put equation and just multiplying this number?
Not sure I got your idea, but I hope you says that we need to take this as a new value of parameter s, new, and we have to solve this Cauchy's problem with this value here. Just solve this Cauchy's problem once again, another time, additional like solution of this problem, and take the result of this solution as a first term in the numerator in this ratio. The second term we already know from the previous solution at sk minus 1 value, and we divide it by this variation delta. This is how we get the derivative, and once we have all these values, we can compute the new value of s. And it can be proven that this iterative process converges to the value of s, which gives us the solution of the original problem. So this is the idea of shooting method for actually for any general equation, not just this linear equation. Okay, I feel it's sort of enough for this part of our class, right? So let's stop here.